electrostatic potential is defined as electrostatic potential at a point P due to an electrostatic field is the work done by an external force to bring a unit positive charge from infinity to the point P without changing its kinetic energy. This is very important. I'm reading it out again. Electrostatic potential at a point P due to an electrostatic field is the work done by an external force to bring a unit positive charge from infinity to the point P without changing its kinetic energy. Now what you have to do is you have to take a unit positive charge and from infinity you must bring to a particular point P without changing its kinetic energy. So that means you cannot give any extra force so that the velocity changes and therefore the kinetic energy changes. So what shall you do? Let's draw it. Suppose this is our reference frame and this is a point charge Q which sits at the origin. This is X, this is Y, and this is Z. And in presence of this charge which creates an electrostatic field, you have to bring a positive charge from infinity to this point P. Okay, then we will get the electrostatic, if we can find the work done by the external force to bring it from infinity to this point P. Let me write it clearly, from infinity to this point P, then the work done will give you the electrostatic potential. Now what is work done? This is our figure, this is the vector R, and the force at P, it will be radially outward force due to this point charge Q at this point P. A 1 coulomb of charge is here, right? It's very similar to electrostatic potential, so you know this. 1 coulomb of charge sits here, or 1 charge. So the force on this 1 charge, unit positive charge, is 1 by 4 pi epsilon 0 q by r square times r cap. It is radially outward. Now, but what you have to do, you have to give a force. You have to give a force from this opposite direction, right? So that this charge from infinity comes and sits over here. Let's draw this figure again. So this is X, this is Y, this is Z. So this is any point R. You are bringing this charge, this 1 coulomb of charge is coming from infinity. But it should not change its kinetic energy. That is the most important point. So what do you have to do? You have to give a force like this, right? In which direction? In this direction you have to give the force, else it will not come. And what is the amount of force you have to give? You have to give this amount of force. See, this force is varying with R. At each point this force changes with R. It is a function of R. So when you bring this charge from infinity to this point P, you have to change your force at each point so that the kinetic energy of that charge does not change. It is written here, see, without changing its kinetic energy. So let's find the work done. See, you have to give a varying force, right? Varying force means each point the force changes. So you have to use calculus. It's no point avoiding that. So what is work done? dW, this is the work done by the external force, this force F. So that is F dot dr vector. Now, there is one concept, there is a concept we must know. This point charge is coming toward the origin. That means r is decreasing, but that will not mean dr is negative. Dr vector by definition is always the small elemental dr times r cap, and this is always directed radially outward. It is always directed radially outward. This is not negative. See, dr, what is dx? It's x plus dx minus x. So what is dr? Dr is r plus dr minus r. When suppose you have a position, this position is r plus dr, and this position is, this position is r, this point is r, and suppose I am exaggerating it a little bit, this position is r plus dr. Now what is this? This length is dr. This is r plus dr minus r. R plus dr minus r. This is the scalar dr. And vector dr is dr times r cap, and it is radially directed outward. Now, so dw is f dot dr, but f is in the opposite direction. If this force is the force due to this point charge q on this 1 coulomb of charge, but here this force is the force I am giving, the external force, right? So that is minus 1 by 4 pi epsilon 0 q by r square times r cap. It is opposite to this r cap. It is negative r cap, right? That's why this negative sign comes, times dr, and dr is dr times r cap. This is by definition positive. By definition of calculus, it's positive. You can't change it. So this is the work done to bring the charge from r plus dr to dr. R means from, suppose it is this position is r plus dr vector, and this position is r vector. So from here to here it is dw. This is work done by the external force. So what's the work done to bring it from infinity to this point? You have to integrate. So this w is equal to integration infinity to this point. So say this point is r, or yeah, suppose this point is r, infinity to r, minus 1 by 4 pi epsilon 0 q by r square. Acha, this is what? R q by r square dr times r cap dot r cap. What is r cap dot r cap? It's unit dot product between two unit vectors, so that will be 1. So that is, take the constants out first, 1 by minus q by 4 pi epsilon 0. This is 1, right? Now you have to integrate dr by r square from infinity to r. So that is equal to, this will be minus 1 by r. So q by 4 pi epsilon 0 minus times minus 1 by r from infinity to r. So that is q by 4 pi epsilon 0 1 by r infinity to r equals to q by 4 pi epsilon 0. First plug this in value, 1 by r times minus minus here, see this minus minus cancels here, minus 1 by infinity, that is q by 4 pi epsilon 0 r. This is the electrostatic potential. This is the electrostatic potential. So V is q by 4 pi epsilon 0 r. Okay, is it clear? This is the electrostatic potential to bring a unit positive charge from infinity to this point P.